Hello friends and welcome to this video. We are with the sixth chapter of our subject Advanced Digital Signal Processing. The chapter here it is titled Adaptive Filters, and to learn the design of the adaptive filters to meet the requirements of the various signal processing applications into the real time, we have gone through several of the topics. So the topics were adaptive filtering system identification, FIR adaptive filters. Thereupon we have been introduced to the very important and the popular algorithms. Those were the steepest descent algorithm, and next to that the LMS algorithm. For the LMS algorithm we have also seen the convergence and its corresponding normalized form here. Now it is time to have a discussion with respect to the most popular application of the adaptive filters. The application is noise cancellation. So here we have the current topic, noise cancellation. As we see the two terms into the topic title here, the first one, noise, it is a kind of the signal but undesired kind here. We don't want the original information to be interrupted, to be changed, to be made false with the help of the unintended signal, which we term as the noise signal. And always in the design of the practical applications we cannot avoid noise completely. Therefore we should have the strategies to remove the noise here. So the cancellation of the noise part from the practical signal is nothing but the noise cancellation here. So here we consider the problem of noise cancellation, where we have the usual notations that we have carried right from the video number 1 from this current chapter here. So the desired signal, which is a discrete time random process denoted by D of n, is to be estimated from a noise corrupted observation, that is the practical signal that we have been denoting it by x of n, the input signal here. So the x of n will be having the two parts. First one is D of n, the desired signal, and the second one is the noise part, that is denoted by V1 of n here. So it is very clear here that without any kind of the background or the information about the desired signal or the noise signal, it is quite not possible to have separation of the intended signal from the noise, what we are intending to practically do here. So here we expect to be given a reference signal that can be denoted by V2 of n, and that is correlated with the noise signal V1 of n. So that time the reference signal V2 of n may be utilized to have estimation of the noise V1 of n here, and this estimation will be further subtracted from the original practical signal x of n here, so that we form the estimate of the desired signal here. See, the estimate of the desired signal can be denoted by d cap of n, and this will be equal to x of n minus the estimate v1 cap of n. So let us discuss the example that if we have the desired signal d of n, then the noise signal v1 of n and the reference signal v2 of n to be the jointly wide sense stationary random processes, and if the statistical metrics as like the autocorrelation denoted by r suffix v2 of k and the cross correlation denoted by r suffix v1 v2 of k are the known quantities, so that time the Wiener filter may be designed to find the minimum mean square estimate of the noise signal V1 of n here. So let us have the illustration of the same with the help of a block schematic here. So in the block schematic on the left hand side upper corner you see there it is the input of the practical signal x of n, which is having the desired signal component denoted by d of n and the noise signal component which is to be cancelled by the use of further the adaptive filtering. Here we are just making the use of Wiener filter here. So the noise component is denoted by V1 of n here. See, this signal is straightly given as an input to a summation here. So we have the plus sign to this summer here, and from this x of n, the information I can call, we have a subtraction. See, what particular thing we are subtracting from x of n? Here it is shown as v1 cap of n, which is the output of the Wiener filter, where the input is provided as v2 of n, what we have called as a reference signal here. So v2 of n is fed as input to the Wiener filter, and it will output into the estimate of the noise signal because of its correlation to it, assumption here. So it is v1 cap of n, which is to be subtracted from the x of n, and finally we intend to expect d cap of n here. Now in practical case, if we have this particular block schematic implemented here, this is having the focus on stationarity assumption here, which is to be avoided here in the practical sense. We have the non-stationarity here. So here the required statistics of v2 of n and v1 of n are generally unknown if we opt this particular procedure here. So therefore there should be any alternative way to have design of the filter. So alternative to the use of Wiener filter that we have shown in this block schematic is the consideration of the adaptive type of the noise canceller. So let us visualize the illustration of the noise canceller in adaptive manner here. So here we have the two input signals. Actually x of n is the input signal, which is having the desired signal component d of n added by v1 of n, the noise component, given as input to the summation here. Whereas v2 of n is not actually the input but a reference signal that is been used for estimation purpose here. So v2 of n instead of the Wiener filter is added as input to the adaptive type of the filter here. See, for the adaptive type of the filter, always and always we have to focus on the error signal, which is obtained from the difference here. So the error signal, it is denoted as E of n. Here we are obtaining it by x of n minus v1 cap of n. So here v1 cap of n is the output of the adaptive filter, where v2 of n is the input here. So this is the block schematic. I hope you have understood, as we are switching from the stationary aspects of assumption to the practical non-stationary aspects here. So if the reference signal that we have denoted by v2 of n is uncorrelated with the desired signal d of n, it will follow the minimization of the mean square error that we have been denoting so far as the expected value of mod square of the error signal E of n is equivalent to have minimization of the expected value of the mod square of the difference v1 of n minus v1 cap of n here. So in another words, we can say that the output of the adaptive filter is the minimum mean square estimate of v1 of n. Now let us come to a discussion of specific example where we have a signal to be estimated of a sinusoidal type here. So the desired signal d of n here we express with the help of the trigonometric sine function. So d of n is equal to sine of n times omega 0 added by pi. So with the value of omega 0 is equal to 0.05 pi, and the noise sequences, those can be denoted v1 of n and v2 of n, which are basically generated by the first order difference equations. Here we show v1 of n is equal to 0.8 times v1 of n minus 1 added by g of n, whereas v2 of n is equal to minus 0.6 times v2 of n minus 1 added by g of n, having g of n the representation of a zero mean unit variance white noise random process, which is uncorrelated with the desired signal d of n here. So by the next illustration for this particular example, we show a plot of 1000 samples of the corresponding sinusoidal representation in graphical manner here. So on the horizontal axis, you see there are the markings from 0, 100, 200, 300, 400, 500 and so on in this manner up to 1000, the extreme right here. Whereas the amplitude of the sinusoidal signal is ranging in between -1 to +1 here. So here it is the desired signal here. And now let us have visualization of the noisy signal, which is the practical signal fed as input to our system to be designed here. So it is x of n, which is having both the components d of n added by the noise component v1 of n here. Now as we have seen the block schematic to be implemented here, if we have the reference signal denoted by v2 of n, that is used for the estimation of the noise signal v1 of n, what we can illustrate with the help of this particular figure. Let us make the use of a 12th order adaptive noise canceller with the coefficients that are updated using the normalized LMS algorithm. The normalized version of the LMS, least mean square algorithm, we are already covered in the previous video here. So that time the estimate of the desired signal d of n, that is produced with the step size, for example 0.25, can be shown with the help of this particular figure. Now you see, after about, for example, 100 iterations, the adaptive filter is now here producing a fairly accurate estimate of the desired signal d of n. And if we double the number, that means after about 200 iterations, the adaptive filter will appear to have settled down into its steady state behavior here. So in this complete process, we have one advantage. The advantage is that this particular adaptive noise canceller, instead of the Wiener filter, can be utilized when the processes are non-stationary, that is the practical reality here. So for example, let us have V1 of n and V2 of n to be the non-stationary processes. Those are generated by the first order difference equations considering g of n that we have represented in the previous mathematical equations to be non-stationary white noise with the variance that will increase linearly, for example the value 0.25 to 6.25. So as earlier, the desired signal d of n is estimated using the 12th order adaptive noise canceller with the coefficients that are updated according to the normalized version of the LMS algorithm here. So here we visualize the desired signal d of n. So it is the earlier representation, the samples 0 to 1000 we have marked for the horizontal axis here, and now we visualize the noisy signal, that it is the representation of the x of n having both the components. Now in this illustration here of x of n, you see the increasing variance in the adaptive noise that you see from the left hand side to the right hand side here. Now the non-stationary reference signal that can be denoted by V2 of n is utilized to have estimation of the noise signal to be cancelled out to be denoted by V1 of n. Here we visualize, and because of this the estimate of the desired signal d of n that is produced by the adaptive filter we visualize here. So as we see the performance here, the performance of the adaptive noise canceller is not so significantly affected by the non-stationarity of the noise here. Now in this case, the success of this particular operation with the use of adaptive noise canceller, the contribution is because of the availability of the reference signal V2 of n that we have utilized for the estimation of the additive noise denoted by V1 of n to be cancelled out here. But practically there are many of the applications where such a reference signal is not at all available, and thereupon we have to opt another approach for the estimation purpose here. So there can be few of the cases where it is possible to have a derivation of the reference signal by the simple delaying process x of n here. We know that x of n is equal to here d of n, the desired signal, and the noise signal v1 of n here. So let us have, for example, the desired signal d of n is a narrow band process and the noise signal v1 of n is a broadband process having the expected value of v1 of n multiplied to v1 of n minus k equal to 0 provided mod k is greater than k0. So if we have the desired signal d of n and the noise signal v1 of n uncorrelated, so that time here we represent the expected value of v1 of n multiplied to x of n minus k equal to the two terms. The first term is the estimate of v1 of n, expected value of v1 of n into d of n minus k, whereas the second term is the expected value of v1 of n into v1 of n minus k, and the addition of these two is equal to 0 provided mod k is greater than k0. So therefore if n0 is greater than k0, so that time the delay process can be denoted by x of n minus n0 samples here. So this will be uncorrelated with the noise signal v1 of n, and it will be correlated with the desired signal d of n here. So therefore x of n minus n0 may be utilized as a reference signal for estimation of the desired signal. So this is illustrated into the block schematic here we see. So here it is the use of adaptive filter here. Now here instead of the implementation type we have discussed here, the procedure will produce the estimate of the broadband process d of n, and the error signal e of n will correspond to an estimate of the noise signal v1 of n. And for example of using this adaptive noise canceller without a reference, let us have x of n is equal to, as usual, d of n added by v1 of n. So d of n, for example, is a sinusoid of a frequency omega 0 is equal to 0.05 times pi, and let us have the noise signal v1 of n to be of the autoregressive type, so AR of 1. So here we have the consideration that g of n is a white noise with the variance of, for example, the value 0.25. So let us see the noisy process, that is the input to the system. So it is denoted x of n, addition of d of n with v1 of n here. So this is the noisy signal here, and the corresponding output of the adaptive filter making the use of normalized LMS algorithm, LMS standing for the least mean square algorithm, having the normalized step size, for example 0.25, and the reference signal obtained by delaying the x of n by n0 is equal to 25 samples here. So here it is the illustration, and you see point improvement as compared to the earlier representation here. So this was all about the application of noise cancellation, the most important and the popular application of the adaptive filters here. So by the next lecture we shall be continuing into the same chapter and will be addressing few other LMS based adaptive filters. Thank you.